going to look at in this course is just a basic overview of what science is. We're going to look at some different terminology that you've probably been using since you were little, and we are going to just get started and warmed up here before we get into some physics. So what is science? A couple things here, objects and properties. Objects are what we look at and what we touch and feel and try to observe. Properties are what these objects have or how we describe these objects. We got a fuzzy bear, we got a titanium bike, and we have a yellow ball. Those would be three different objects and one property of each object. So you can have two of the same object, like two bears, and they can have two different properties. So a bear would be a fuzzy brown bear, or maybe you have a wooden bear. So you'd have two of the same object with different properties. So when we describe things and we collect data, we can look at the same situation and get things with different properties. Referent is an important term. A referent is what we compare it to. So if I measure a boat and I say it's 30 feet long, the referent is the foot, that's the unit. You have to make sure that you have the knowledge of what the unit is. If you don't know what a foot is, then a 30-foot long boat doesn't really do anything to you. In this class, we use the metric system. So a lot of the things in the metric system you may not be familiar with, like a meter. So when we talk about a meter, a lot of people just refer to it as a little bit bigger than a yard. So a meter is an actual length that has been measured, and there's a group of scientists that have determined exactly what a meter is. So when we go to measure a meter, that's what we're referring back to. Like a kilogram. Here on the right, you can see inside those vacuum tubes there's a piece of platinum in there, and that platinum scientists have determined is exactly 1 kilogram. So when we refer back to a kilogram, that's what we're referring back to. Every single unit has a referent. So seconds, amps, all these different things have a predetermined size that the units refer back to. And that's what we mean by referent. Scientists collect data. Data is what allows us to make conclusions. We look at the data and we come up with conclusions on how the data works or why we got this data or what we're going to do with this data. So data is what we collect. One of the problems with today's society is we are only collecting selected data. We only look at it from one side. So I know in America, we have a lot of issues with the news, right? You have Fox News, you have CNN, and these two things, because they're tied so closely to their political parties, are only looking at parts of the data that help promote their political party. So it's very difficult to get information from those news sources that's very scientific, where all of the data has been looked at. A lot of times you'll look at a third party source like Johns Hopkins or maybe even the BBC News Network, somewhere from outside of the States where they're looking at all of the data and not just a select amount of data. But data is what we gather, data, we put it together, and from the data, we draw conclusions and try to understand what's happening. Symbols and equations. Symbols are what we represent in formulas. Just some common symbols here in this chart. We got the infinity symbol. We have a theta, which would represent angles. You see the pi symbol. That symbol on the top left, that's a lambda. That's going to represent wavelength. The symbol that looks like a P, that's actually a rho. A lot of our symbols are Greek letters. And we're going to use these symbols in equations. Equations are mathematical relationships between properties, but what that really means is that equations are ways for scientists to simplify a sentence or a definition. For instance, let's look at velocity. Velocity is how fast you cover a distance or the rate a distance is covered. So the equation for velocity would be v equals delta x over t. And to a scientist, a delta means change, and it's like a triangle, it's a Greek letter. So the delta x would be your change in distance divided by your time. So we're just going to shorthand a long definition of a thing and just put it into a simple equation, or not so simple equation, as you can see here at the bottom of the page. Proportionality. The symbol between A and B, that's a proportional symbol. So in this case, we say A is proportional to B. As one thing goes up, the other thing goes up. Um, you will see this when you're reading blueprints. When you read the blueprints, you use a scale ruler. So all the blueprints are scaled down to 1/8, so or 1/12 or whatever you happen to be reading. So what that means is for every increment on the blueprint, that represents a foot on your actual measurement or whatever it happens to be. So you're going to change these measurements as you read your blueprint. So you're going to scale it down. So every eighth of an inch is equal to a foot. And you can just see this picture with his dogs where you can set up a proportion. 10/20 is equal to 15/30. You can see in both cases it's a half, so 20/40 and 25/50, right? Those would be equal scales or directly proportional. As one thing goes up, another thing goes up. Like the amount of ice cream you eat is directly proportional to um, how much weight you're going to gain in most cases. Inversely proportional, that means one goes up and another goes down, like a seesaw. Something increases, something else decreases. So as your spending increases, your bank account decreases. That would be an inverse proportion. Mathematical constants, these are things that have been determined through experiments. Pi, 3.14159, and it goes on forever and ever. That is actually the ratio of the circumference divided by the diameter of every single circle. Those are mathematical constants. We'll talk about the acceleration due to gravity. G is negative 9.8 meters per second squared. That's a constant. The universal gravitation constant, the charge of an electron, these things are all constant values that don't change. In this case here, we're looking at a precise shot. Precision and accuracy sometimes get confused. Precision is how close the measurements agree with one another. So in here you can see a very precise grouping where all the arrows are hitting the same spot. They are not, however, accurate. An accurate shot would hit the red bullseye. So you can have a precise measurement or something can be precise without it being accurate. A scale, for instance, can measure the weight correctly, but if you don't have that scale zeroed, you're getting the wrong weight every single time. Same thing with your rifle. If it's not sighted in, you may be the best shot in the world, but you're not going to hit your target if you don't have your sights set correctly. Accuracy is hitting where you want to hit, hitting the bullseye. So this is how closely they agree with the measured value. We'll do a lab later this semester where we try to determine gravity, and our value wants to be the acceleration due to gravity at negative 9.8 meters per second squared. Will we get that value? Probably not, but our goal is to make it as accurate as possible. A pseudoscience is something that's misleading and wants you to believe that it's scientific. It sounds scientific, but it's really just a farce. One of the best examples of this is the weight loss pills and the weight loss supplements. What they'll do is they'll take somebody who's in really good shape, they'll feed them a bunch of junk food, and then have them gain a bunch of weight. So they take two pictures, a picture before when they're in good shape and a picture after they've eaten all the garbage. And then they'll put them in a magazine and say, if you take this pill, look how much weight you can lose, and they'll just flip flop the pictures. So it's the same person, but the before and after have been reversed. Some people think global warming is a pseudoscience. There's a lot of speculation that man-made global warming is a myth, that it's not actually true. So some people would call that a pseudoscience. Scientology sounds scientific, but it's just a giant pyramid scheme for rich celebrities, it seems like to me. And then snake oil. You may have heard of a snake oil salesman. These were people back in the colonial times who would drive around and sell ointments and healing creams and healing drinks and things that they would claim would make you better if you were sick, but they really didn't do anything. So that's what pseudoscience. So be careful if you're looking at scientific data. Make sure it's peer reviewed, especially in today's day and age. There's a lot of information out there, and if scientists aren't peer reviewing it and multiple scientists aren't coming to the same conclusion, it may just be a pseudoscience. So be careful what you read on the internet. Models and theories. We're going to look at theories first. A theory theory is a broad set of working hypotheses. It has a lot of experimental support, but it's not a law. It's not proven to be true time and time again. So a theory is really what you come up with, a thought experiment. A lot of math will be involved. Maybe like Charles Darwin, a lot of research was involved, a lot of data collection was taken, and that would give you the theory of evolution. Einstein's theory of relativity, of general relativity, that's also a theory. But again, these things are nearly impossible to prove. There's no way to prove that man came from apes, right? That's a theory. Now, we know evolution takes place. We know survival of the fittest takes place. We can prove that by looking at different insects and animals over time and just seeing how they evolved. Evolution is something that is true, but the theory that man came from apes, that's just something that they think just based on different skulls and such, but there's no way to prove it. Einstein's theory of relativity, again, the math works out, the thought process works out, but there's really no way to prove that theory. So theories are legitimate, but they just can't be proven enough to call them laws. A model is something that allows us to see a very large or a very small system in greater detail so we can analyze it, like the model of a solar system. We can't really look at the solar system in one big picture, uh, but if we create a model, we can see how the solar system works together. Likewise, if you're at the doctor's and you're getting a checkup and there's something wrong with your nose or you have a sinus infection and the doctor wants to show you, he can't actually show you inside your nose. So what he does is he shows you a model of your nose and explains where the situation is taking place. And then down there you can see the picture of the DNA molecule. Again, something very small that we make more life size so that we can explain it and understand it better. Laws and principles. So laws and principles are things that hold true time and time again. The laws of nature or the laws of physics are what govern all of physics and all of nature, and if they're broken, science breaks down. So laws are definite, they're set in stone, and we have to obey them. They've been both proven mathematically and experimentally, time and time again, and they always hold true. Principles are just small laws. They're things that we know are true. We know that they can't be broken, but they're much more specific. Like Bernoulli's principle is one specific law about how pressure and velocity work together. So we'll talk about that later this year. But principles and laws are kind of confusing. Laws are very large, like the law of gravity. The law of universal gravitation covers the entire solar system, where a principle is going to deal with one specific issue. And the last thing we're going to look at is the scientific method. This is a thought process that scientists and every human goes through when they're trying to explain a situation. So there's a 5-step plan. First, we observe some aspect of nature. We propose an explanation. Why did this happen, do you think? We make predictions. What do you think is going to happen in the future? What do you think is going to happen with our experiment? We test out the predictions. This is where we gather our results and we do our actual scientific investigation. And then the 5th step, the last step, is to draw a conclusion. So we do it all the time. One thing we could just make up a thought process here is what are the conditions for rain? So that's an aspect of nature. Every once in a while it rains. Why does it rain? So we propose an explanation. Why? I think it rains because there's a lot of clouds in the sky. So I'm going to make a hypothesis to say when there's 70% cloud coverage, it's going to rain. That's my prediction. So over the next month or 2 months, every day I go outside and I measure the amount of cloud coverage in the sky and I determine if it rains or not. So I have a little journal, I write down some notes, and at the end of 2 months, what I do is I notice in my journal, oh, if there's 100% cloud coverage, it rains for sure. If there's 90% cloud coverage, there's a chance of rain. If there's 80%, there's a less chance of rain. So then I come up with a conclusion that says, I conclude that 70% cloud coverage only has a 25% chance of rain. So my experiment showed blah, 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 and this is what you would publish. And then other scientists would look at it and determine if it's repeatable, because you always want to be able to repeat your experiments. So that's the scientific method. It's just a method of analyzing a situation. It just formalizes what we naturally do.